Dr. RS Sharma, who is Assistant Professor in the Department of Mechanical Engineering in the Albag Educational Institute. He has been a visiting scientist at the National Polytechnic Institute, USA, and also have been to Center of Metal Forming at Sofia, Antipolis, France. His main research interests include bulk nanomaterials through severe plastic deformation, multi-scale modeling, intelligent manufacturing, and soft computing. He has incorporated the agility in forming industry and novel design philosophy that is based on intelligent knowledge based on the systems for enabling rapid redesigning of the existing production systems. I now request Dr. RS Sharma to please present his talk.
So, why we require light material? This is a metal tetrahedron which shows processing, microstructure, properties and performance are totally interrelated. If you want to enhance the performance, we have to enhance the properties. If you want to enhance the properties, we have to fabricate the microstructure, and for that we have to go for some kind of processing technique. So, performance is related to microstructure. So, why we require this kind of material? Because day by day the challenge is to optimize the processes, to optimize the products, to scale down the size, plus to get a lighter weight. So, the application of this ultra fine grain material is in defense applications, and especially is in medical implants. In medical implants, they are manufactured by titanium. So, if we are able to fabricate, if we are able to decrease the weight and increase the strength of these medical implants, it will be a great effort. So, our research focus on this scale. At present, we are in microns. The structure is in microns, and we want to take it to decrease the grain size. So, this is the classification of some materials: coarse grained metals, ultrafine and nanometals. So, the material which we get in ready-made, that is coarse grained material. So, what we are in process? We are in process if we can decrease this, if we can bring it to ultrafine grain material. So, by that what happens? So, this is the graph which I have taken from the literature, that is from Langdon 2007, which shows that two graphs for stress and strain are compared for coarse grain and ultrafine grain materials. So, for UFG it can be seen that it has got higher yield stress. It has got higher yield stress. So, where our work falls? So, our main objective is to decrease that D. To decrease that D is basically the grain size. So, we are not really working on the nano scale, we are working on bulk nanomaterial, means all the dimensions are not under nano size, but we are working at a microstructure if we can decrease that D, if that D can be brought out to some 100 nanometers. So, again the objective is to, this is the larger grain size, smaller grain size, if we can find the grain size. So, there are two approaches for this, to reduce the grain size. So, there are two approaches, one is top down approach and other approach is bottom up approach. So, we are not falling under bottom up approach, we are only in top down approach. In top down approach, we have got number of techniques are over there: ultrasonic short pinning, ball drop test, air blast short pinning, ball mill, high pressure torsion, sliding wear load, ECAP and RCS. Again, we are into severe plastic deformation only, that is high pressure torsion, ECAP and repetitive processings. So, these are the different techniques in severe plastic deformation. There, one is high pressure torsion. So, in this what is being taken, a simple sample is being taken, and it is being provided a torsion between two dies. Then we have got repetitive corrugation straightening, and it is used for converting the grain material for sheet metal. One more SPD process is, that is cyclic extrusion compression. Next one is multi-axial forging, high pressure torsion, already I discussed, ARB accumulated roll bonding, and this is for sheet metal, that is rollers for RC repetitive corrugation and straightening. Next one is constrained groove pressing, and one more, that is ARB. So they all fall under SPD process, severe plastic deformation. Okay. So but our work falls under ECAP. ECAP stands for equal channel angular pressing. The main objective is, so this is it is a SPD process, and this is one of the best SPD process which I have discussed just now. So this is the generic view of this SPD process. So what happens, the basic idea is to place a coarse grained material over here, press it through other channel. So this is the shear zone. So at the shear zone, high strain is because there is a turning angle of by 90 degree or some maybe some other angle, it can be that is given by an angle of intersection. So high deformation takes place at this place. So at this place what happens, immediately the strain is induced. So when the strain is induced, what happens, it is hitting the microstructure. So in this way what we can just by inducing the strain we can reduce the grain size. So in this process, the beauty of this process is this, that we are getting the same blade, the cross section of the blade remains same. The cross section of the blade remains same, but what has achieved, we have achieved the higher strength. And this again number of passes can be done. Number of passes can be done because this blade has come out, then again we can put it again the same process can be done over here, then again. So number of passes can be done, and over the time what happens, we can achieve a higher lower grain size, and lower grain size is basically that. So I forgot to discuss this one, there is one relationship, that is sigma y is considered sigma d root times d. So our research area totally falls under this category, that is a Hall patch relationship. This is a Hall patch relationship. The foundation of our work is on this equation only, that is Hall patch relationship, which shows that the yield strength is dependent on, this is basically an inverse square root law. If we can decrease the d, we can achieve a higher strength. So in this case what we are inducing very huge shear strain, because immediate, as it turns back, immediate deformation is taking place. The basic objective is to develop a metal forming process where high strains may be introduced into metal blades by simple shear. This is what I just told you about that Hall patch relationship. So what are the main advantages compared to other processes of top down approach? Like in other techniques, the main is multiple passes through ECAP is possible. The biggest advantage of this is can be conducted at room temperature, can process large bulk materials. ECAP processes have significantly enhanced properties. So I just discussed about that repeated passes can be done, pass 1, then we can go for pass 2, again that billet has gone again, then again we are getting a refined microstructure, then again third pass we can go for a third pass, then again we can go for a fourth pass. Now our research focus comes here, where our research focus is how to optimize this process, how to get a best process among this, because this process depends on number of parameters. The number of parameters are, you can see from here, one is in angle of intersection, the other is outer arc angle, third process variable is that is velocity of pressing. These are the three. Then the fourth variable is the friction at interface of this workpiece and die. So our aim of the research is basically which is the best angle where we can get the maximum change in shear strain. So whether it can be at size 0, whether it can be at this, or whether it can be at this. Because this is the relation on which this entire is depending, that is equivalent strain is given by this, and again angle of intersection and outer arc angle both are coming. So we can say the equivalent strain is a function of that, just now I told you about this angle of intersection and the other, that is arc angle. One more process that can be done in this ECAP is we can follow number of routes, because we have to make sure that the grain refinement is uniform. If we are again putting again and again in the same direction like head and tail, then again head and tail, again head and tail, So, but again in that cases what is being shown in the results is that we are not getting a uniform microstructure. So, for to make it sure what we can do, we can follow different number of routes, that is just changing the orientation of the billet that is coming out, and again changing the orientation, then again it is putting it aside. This is one more variable that is in ECAP. So, this is the experimentation dies that we have doing at DI. This is these are the samples that we are getting out of it, and this is a very small concept that I have shown through a plasticine, just to convince you, because in this we cannot see the microstructure by these naked eyes, but here I just to show the concept how this shear of material is taking place. Just I have taken a plasticine, this was first pass, then again it was pushed, again we are getting more shear strain, then again in the third pass, then in the fourth pass this concept was shown just by through a plasticine. Okay. So, just now I told you that my research area falls under what should be the best possible process parameters by which we can get maximum equivalent strain. So, we have tried number of options. These are FE simulation results for number of dies, for number of velocities, for number of frictions. Okay, these are the forging force requirements that we are getting. These are the results that we are obtained, because we are in the process. Because I just would like to add one thing over here. Among these SPD processes, none of the process is commercialized till date. None of the process is commercialized till date for grain refinement. And I told you about there are number of SPD processes are there, RCS, that's HPT, then this ECAP, then accumulated roll bonding. Among all these processes, ECAP has got potential for commercialization. The reason is that because in that we can put a bigger size of billet, in RCS we can put only sheet, in HPT we can put a very small sample only, but in this we can go for a commercialization. These are the results that I have taken from Velab, just to convince you that this was the original specimen of copper. Yield stress of 80. After ECAP 2 passes, we are able to get yield stress 320 megapascals. Then after 16 passes this, and after 16 passes this. This was 14, and this was without back pressure, and this is with back pressure. So again, as our main aim of the research is to commercialize this process. Okay, because again and again we are putting 10 mm, 20 mm, and if we are again repeating 16 passes, 20 passes, what is going to happen? It will be very much time consuming. So if we can redesign this ECAP process, that in one go we can achieve higher strain rate, because in this case we will get some strain rate 1.15, then again we have to pass it, then again we have to pass it. So why can't we design some kind of process in which in one pass only we can get a strain of 3.45? So whether this is best, or which one is best? These are some proposed designs that we have discussed. So I'll show it here, that 2-ton ECAP that we have tried this, and this has not been reported. So this is the FEM simulation for ECAP 2-ton. This is a concept, because in the normal ECAP only one pass is given. Again in this, in a one through we are getting double, 2 passes we are getting again. But the problem is this, in the billet get fixed. For getting it out, what we have to do? We have to put one more billet, then the first one will come out. Again we have tried, because till now the angles that has been proposed even in the literature are this or this or this, 105, 130, 140, 150, like this. But again now recently we have just designed this one more. Why can't we have this kind of? And really we have got a very good results for this. We have taken a 65 degree, and this is a pass 1 result. We are able to achieve 2.1 equivalent strain. This is for pass 2. We achieved 3.7. In pass 3, we achieved 5.5 for this. In pass 4, we were able to achieve 7.5 strain in this, and this is not being reported till now. One more, this is the 4 passes complete results for 4 passes. For the 65-degree, first pass 2.1, that just it's a repetition at one place. Then second pass is there, 3.7, then the fourth one, and then the next one. So we are getting 4 passes in this die. One more option that we have tried is, why can't we have this kind of design? That's a U kind of die, but again it has got some problems in commerciality that we are facing it. That is, again the billet gets stuck inside again. But in this we are able to obtain very high amount of equivalent strain. So in this again we have taken 2 kinds of this. I'll just refer it, that at one place we have given the chamfer, in the other we have given a curve, and again we have seen that equivalent strain is affected by this small parameter also. So we are able to get very good results in this, but again we are facing, because in this case what is happening, huge amount of force is required, huge amount of the energy requirement is high, and the second thing is that the billet is getting stuck it inside. So for that, to bring it out, we have to put again one more, that it comes out, then it comes out. So this is the second option that we have tried. This is with the earlier one was with chamfer, and this one is with fillet. I'll just show you one pass. This is one more we have tried, is this, we have used rectangular billet, because in the literature we have seen only square billets or circular billets, and this effect has also been studied here for rectangular billet. So in this case also we are getting higher amount of strain, but all the passes are not being attempted till now. This is one more, this is an enhanced version of 2 ton. We have given a 4 tons, 5 tons, and this has got, because what I told you just now, none of the SPD process is commercialized. So for commercialization, what has to be done, that we have to make some, we have to basically increase the efficiency of the process, basically efficiency of the process, how fast we can get the product. So just to reduce the number of passes, because that microstructure refinement is depending on number of passes. In industry, what you cannot expect that again and again you are repeating the same process. So again this is one more complicated die, and we are getting this die fabricated. So because through simulation we have arrived some good results. But in this case, one more problem that we are facing is this, because at these turns the cross section is more than at the normal. So the next billet that is required is of higher length. This is till now what I was saying, that was only 2-dimensional dies, and this is again this is a 3-dimensional variant that I am showing, because we have given in 3 dimensions. Like to overcome that problem of stucking. So what we have got, this the commercialization is very difficult for this, because we require 4 pressing thing. So what we have shown, this was a single ton, 3 ton. Now again what the recently that what we have proposed, just to avoid that problem of stucking, we have provided 4 plungers. I will make it clear in the next one. So we have provided plungers at 3 places. Now the second plunger comes into force, then the third will come into force, then this fourth will come into the force. So just to overcome that problem of stucking, but commercialization of this is quite tough, because we require 4 prime movers. This is the finally it comes out. So these are the results that I've just discussed. Ki what is the effect of different angle of intersection, angle of outer arc angle. So for various velocities, for various frictions, this is what. Now this is a total novel idea that we are proposing is, because up till now whatever I have shown, again that is a discrete process. It is not a continuous process. Discrete is in sense that we will get one billet only at a time. Then again we have to feed other billet. Then again we have to feed third billet. But again that also creates a problem in high production rate. So this is the more recent idea that we have proposed is, if we can have a continuous feeding in ECAP. So this will be the ECAP die, this will be the rollers, and we will be feeding the continuous bars through these rollers. So this video is quite time consuming, it's very high, because feeding it very slowly, then it will come inside and it will take a turn over here. So this is the recent idea that we are putting just for the sake of, not for the concept of microscope, but the sake of the commercialization of the process. Because that remains same, that hall patch problem remains same, but just to you have to enhance the commerciality of this process. So this is just to convince you all that how this field is coming up, because in outer circle what is that bottom up approaches are getting more popularized, but these top down approaches for getting nanomaterials, bulk nanomaterials is also getting a very good prominence, and this can be shown by number of conferences, number of committees, and number of the proceedings to see. And this is the recent conference that has been happening on nanomaterials by severe plastic deformation. Okay, so the conclusion is there. Conclusions are, a new discipline of metal forming technology is being born, because in the beginning of the lecture I told you it's a merging of manufacturing process and material fabrication for reducing the nanoscale size for devices of any material. This is the usefulness of FE analysis developing practical ECAP process demonstrated in the talk. A dominant experimental process is ECAP in terms of deformation. ECAP refines grain structure without changing the billet dimension. This is the beauty of this process, because the billet can be used for production of anything. It can be a fastener, it can be medical implants, or it can be anywhere in aerostructures. ECAP can reduce grain size to sub-micron range, even nanometer range, depends on number of parameters that I have put asterisk. Grain refinement depends on angle of dies and rotation of billets along with strain. Strength of material increased with each pass. Large equivalent strain is achieved in modified ECAPs. Modified ECAPs that I have shown you, 65 degrees, 2 tons, 3 tons, 4 tons, there we are achieving higher equivalent strain, and continuous process are most likely to find practical application. That last one that I have shown. Thank you, sir.